Hello, I am the moustached Mr. Daycock, and today I'm going to be teaching you about the power rule for differentiation. Now, in the last video, I told you what the power rule was. So the power rule is this, as a reminder: if x is equal to t to the power of n, where n is a constant, just a particular number, then dx by dt is equal to n multiplied by t to the power of n minus 1. And that is your power rule for differentiation. Now, it doesn't have to be x and t, so very, very often the two that you used are y and x. So if y is equal to x to the power of n, let me change the colour there, then dy by dx is going to be equal to n x to the power of n minus 1, or in fact any other variable at all. Let's say just pick two randomly out of the air. Let's go with a and b. Let's say we had a, where a is a variable. Often a is considered a constant, or a letter to be used for a constant. But a equals b to the n. In this case, a and b are variables. Then dA by dB is going to be equal to nb to the n minus 1. And the variables we pick really don't matter. The principle is exactly the same. In each and every case here, n is just a number. It's just representing a constant number, whereas here x and t are variables, here y and x are variables, and here a and b were the variables. And I put b in the wrong colour. Let me change that. There we go. Okay, so let's actually see how that works in practice with 7 different questions. So here we have y equals x to the power of 7. So we have y equals x to the power of 7. And our power rule tells us that dy by dx is going to be equal to, we have to multiply by that power. If we go up here, look at the rule, the n comes down in front as a multiple. So we multiply by that power, so we can put that 7 in front. Then the x is still there. And then it has to be raised to the power of n minus 1. So that's 1 less than whatever n was. And 1 less than what 7 was is 6. And so our rule is very simple here. dy by dx is 7x to the power of 6. Okay, what about over here? We've got a slightly different situation. Here we've got u and v, and we want to find du by dv. So let's write this out. So we've got u is equal to 3 lots of v to the power of 5. Now the 3 in front seems like, oh no, what do I do? But actually it's barely important at all. Because what you're going to get is you're going to get du by dv is going to be equal to, well, the 3 is still just there. We're just multiplying by it. So it's still kind of there, multiplied by, and we apply the rule to everything else, 5v to the power of, and we have to subtract 1 from that, 5, so 4. 5v to the 4, and it's just 3 times all that, because the 5 is coming down and just being an extra multiple there. And so we get, finally, that's equal to 15v to the 4. So these are your 2 basic examples. These are the ones that show you very simple principle at work here of how we're bringing the multiple down and then bringing that power down as a multiple and then subtracting 1 from it on the power. So this is your basic starting off point. Now we're going to go into slightly more complicated areas, slightly more awkward things which are going on. Now, here we've got x and t, just like in our original ones. This is about, it's asking us to find velocity here, dx by dt, where x is position. But our problem is not that. The problem is the form it's written in. So we have x equal to 1 over t cubed. And this looks like it's fine. It looks like it's in exactly the situation we want. But we never found a rule for what happens when we deal with 1 over something, when we deal with a reciprocal type function. This is all when the function is just a simple power. So what we're going to have to do is turn it into a simple power. And there is a nice little rule for this. If you've got 1 over something, it can be rewritten as x equals t to the power of minus 3. And that's one of our power rules, and it's an important one to remember for dealing with something like this. So x equals t to the power of negative 3. And now we can apply the rule. So dx by dt is going to be equal to, we bring that negative down, and then we subtract 1 from power. But remember, the power is already negative, so when we subtract, we actually get negative 4. So not negative 2, it's tempting to say negative 2, and we get negative 4. And then you could simplify that and return it back to fraction form, in which case you'd get minus 3 over t to the power of positive 4 if you return it to the fraction. So there's an example of a fraction being a little bit awkward. Now, this one down here, y equals 5, find dy by dx. Now this one seems a little bit awkward because there's no x there. What we're going to do is we're just going to carry on exactly as we were and go y is equal to 5, and we want to find dy by dx. But where's the x? Well, the trick is to think of this as 5 times 1, which is of course entirely correct. 5 times 1 is 5. I haven't changed anything there. I haven't made anything untrue. But then remember that x to the power of 0 equals 1. And so I'm going to rewrite that 1 as x to the power of 0. So this is actually y is equal to 5 x to the power 0. Now what am I going to do? Well, I'm going to do exactly the same thing. dy by dx is therefore going to be 5 multiplied by 0 x to the power of negative 1. But I'm multiplying by 0, so in fact dy by dx equals 0. And now you can do this every time. You can think of it as to the power of 0 every time. But a lot of people at this point just go, well, if y is equal to some number, just some constant here, we'll call it c, then dy by dx equals 0. A lot of people just like to think of it as a rule. If this is just a number, then you just get 0. Okay, let's get slightly more complicated again. Here are a few different more ones. Y equals a square root of x, find dy by dx. I'm using dy by dx a lot because although it can be any variables, you'll find that dy by dx is the standard one, and then sometimes you get dx by dt if you're dealing with velocity and position and things like that. And sometimes you'll get a whole load of different things. Maybe you'll do change in temperature over time, so you might have dt over dt if you're dealing with temperature. But for the most part, when you're just doing a little bit of maths and differentiation, we deal with dy by dx. And we'll see why in the next video. But for now, most of these are written as dy by dx to emphasize that. Okay, now for this one, we're going to have to use our power rules again. We want to remind ourselves, and I'm going to leave the colours alone a bit for now and just go on to the algebra. I'm going to get y is equal to x to the power of 1/2. We need to remember that a square root is the same as a power of a half. And therefore, dy by dx is going to be equal to, well, we have to multiply by that half and then subtract 1 from the power. So it's x, and what is a half take away 1? Well, it's negative a half. So our dy by dx is a half x to the negative a half. Now, this situation here, we've got lots of addition, but in fact, if you remember, our whole idea of this is defined by adding up and subtracting functions. We have that whole function subtraction on top, and because addition and subtraction are commutative and associative, that rule still applies. And effectively, when we differentiate something with pluses in or minuses in, we can just differentiate each term. And so we've got p equals this, and so dp by dq is going to be equal to, and we just differentiate each one. Q squared differentiated with respect to q, noticing that it's always we're differentiating with what's on the bottom here. Differentiating with respect to q gives us 2q. 5q differentiated with respect to q. Well, actually, let's take a moment there. 5q, what's the power here? Well, it's a power of 1. So we're thinking of this as q to the power of 1. And so it's going to differentiate to 5 times by 1 q to the power of 0. Q to the power of 0 is 1. So this is 5 times 1 times 1, which is just 5. So this is going to become just 5. And again, that's another rule that people like to remember. If you've got y equals just some constant times by x, then dy by dx is going to be just that constant. Basically, the x disappears, or you can think of it as x to the power of 1, and then see that that power becomes 0, and so the x disappears either way. However you like to remember it, the key point here is we're going to get 5. When we differentiate that 5q, we get 5. And then lastly, when we differentiate the 6, we get 0, and it disappears. So another rule you might want to write down and remember. And then on to our last problem. Our last problem isn't really any more difficult than the previous ones. We've got y equals 3x cubed minus 5x plus 3 all over x. And what are we going to do? Well, we actually just want to distribute this x. And this is sort of like reverse adding fractions. We know that 3 over 5 plus 4 over 5 is going to be 7 over 5. Well, that also means that 7 over 5 can be split up into 4 over 5 plus 3 over 5. And that's what we're going to do here. We're just going to split this up. And so this y is going to be equal to 3x cubed over x minus 5x over x plus 3 over x. And each of these we can simplify its own way. X cubed divided by x, we're going to get y equals 3x squared minus 5x over x. That's going to leave us with just 5. And then the 3 over x, well, we're going to rewrite it just like we did before and write it as 3x to the minus 1 so we can differentiate it. And that will give us that dy by dx, well, the 2 is going to come down. So we're going to get 6x, and then we subtract 1, so it's x to the power of 1. But I don't need to write the 1, so get rid of that. 5, when we differentiate, it's just going to disappear. So we're going to get plus 0, or minus 0 if you prefer. And then we bring this down, we're going to get plus 3 multiplied by negative 1x to the power of negative 2. And so simplifying that, we get 6x minus, the 0's disappeared, 3 times by negative 1 is negative 3, x to the minus 2, or if you want to write it back as a fraction, 6x minus 3 over x squared. And that's probably your most complicated one. A lot of them are not going to be that difficult. But there you go, that's 7 examples of how to use the power rule for differentiation. Thank you very much for watching, and I'll see you in the next video.